Okay, ladies and gentlemen, good morning, very good morning. Today is Saturday, 1st July 2023. This is the first webinar of this month. We have over 725 people who are registered. So we're expecting at least 70% to turn out for this webinar. We just finished on Thursday on HPI, Hospital Audit, Electrical Audit course that is been initiated by AHP and NFE. So we have over 500 participants there. And today, very specifically, we are talking about electrical safety, Earth and Unearthed system. Today's speaker is Mr. Shivakumar. And in this session, we will explore the significance of Unearth and Earth system in various industry, discuss its practical application. Understanding the importance and practical application of these systems is essential for electrical engineer, installers, and professionals working in various industries. We hope this webinar provides valuable insight and encourages further exploration of Unearth and Earth system in your perspective field. So once again, thank you very much for joining, and we look forward for an interactive, informative discussion. This whole webinar is an initiative of National Federation of Engineers for Electrical Safety. I'm aware most of our participants today are member of NFE. It is just a 4 months old association. Within this 4 months, we have done over 6 seminars in all over the country, and we have now started webinars for over 6 webinars. So in very short period, we are able to cover almost 11,000 people in various subjects that we are talking about electrical safety. So we are a group of passionate electrical engineering professionals working in the field of electrical safety. Our members have decades of experience in working with electrical inspectorate of state, central government, electrical designer, MEP consultant, safety officers, and in the field of quality and standard. Vision is very clear. We want to make our nation electrically safe. So the recent introduction of NEC, National Electrical Code 2023, and CA Regulation 2023. So we are doing mass awareness program about this standard. So today, I will be the host for today's program. I come from a fire background for over 34 years. I'm a founder and past president of FSA, Fire and Security of India. And we also have an association called Forum of Critical Utility Services. And of course, National Federation of Electrical Engineers. I am responsible in conducting programs and events, and also taken the responsibility to go global, to bring in all the professional world across under NFE. Today we have Mr. Shivakumar. He was the training professionals in L&T. And he's also a proud member of NFE. He has over 40 years of experience of a wide variety of low voltage, medium voltage, high voltage, extra high voltage, electrical equipment in various electrification projects and process industry. He has been conducting training programs on various electrical engineering topics. As I said, he worked as a manager training with Switchgate Training Center of L&T. We are expecting our moderator, Mr. Gopakumar, to join today. He is in Bangalore. He is with Institute of Engineering. Invited where ministers and state government of Karnataka are known. I now invite Mr. Kumar to talk about the topic that we have highlighted today. And I request all the participants to put your question answer only in Q&A.
Yeah. So many
Okay,
things are
please
there.
put your question in Q&A chat box. You cannot put any question in chat box. I now welcome Mr. K. Shivakumar to take it forward. Over to you, sir.
Yeah, good morning. My name is Shivakumar, and I'm an electrical engineer having more than 40 years of experience in various aspects of electrical engineering, like right from design to commissioning to operation maintenance. At present, I am working as a freelance consultant, and I am giving consultancy to a couple of switchgear manufacturing units in my native place, Salem. And I have been handling training programs in L&T. I was about 10 years, I was a training manager for L&T, and earthing is one of my passionate subject. Today, okay, whatever maybe the topic say, but earthing is such a vast topic. We used to talk 18 hours on earthing. Our course syllabus was to introduction to earthing itself was around 18 hours. But in this 1 hour, to make a start with, we will discuss unearthed system. We will analyze unearthed system. And maybe in subsequent webinars, we will discuss earthed systems one by one. So today's topic of discussion will be unearthed system. Please reserve your question answers. I'll be open to answer your queries at the end of the session. So we will move forward to the session. Today's discussion will be on unearthed system. As you know, the definition for unearthed system is it is a system of conductors in which there are no intentional connection to earth. As you know, in an earthed system, we intentionally connect the source neutral to ground. But in an unearthed system, we do not make any intentional connection to ground. So an unearthed system is, we don't make any intentional, maybe unintentionally during faults, there may be a connection established with the earth, but we do not do it intentionally. This system is classified as unearthed system. So generally the scheme will be something like this. There will be a source may be a transformer or a generator, a three-phase 4-wire system or three-phase 3-wire system, or with a distributed neutral or without distributed neutral. The neutral, as you can see, is not earthed anywhere in the network. A typical scheme will be like this. So even though we say
Sir,
there is no,
I'm sorry to interrupt, sir. Screen varle, sir.
Screen
we can't see. No, we can't see the screen. You are not sharing. You have to share.
I will share. I have shared it, sir. It is showing sharing in my area. It is showing sharing. Screen. So share the report. Another one, sir. Sir, can you see now? Hello?
No, not it. Not it, sir. The screen is not yet shared.
One minute, sir. My IT man is coming. Just a minute.
So very happy to see we have around 300 participants are very keenly watching Mr. K. Shivakumar's presentation. So we are having a technical issues in sharing the screen. In next couple of minutes, we'll have the screen. Yes. Can you make it full screen?
Full screen. Slideshow.
on the bottom right side, full screen.
கப்பு மாதிரி இருக்கு பாருங்க, அதை போடுங்க சார். அதான் அது ஸ்லைட் ஷோ கப்பு மாதிரி இருக்கு பாருங்க.
அது correct. Yeah.
Okay. Now you can see.
No, still not full screen, sir.
Full size is coming in my computer. Full size is coming.
Sir, 61%. It is showing a 61%, sir, on the bottom of your screen. So you have to make it 100. I guess. No, you have to
It
make
is
it
not
100.
at share on the full screen now, Lakshmi. We can see the rest of the slide also on the left side.
Yeah.
It is not a full screen. Please make it full screen.
In my computer, it is showing full screen, sir.
So the
No, we
next
can
two
see all
comments,
the
no, the
slide on the
third
left
one.
இல்ல இது அப்படியே
Sir, from the comment, the third icon you have to click, sir. That book kind of a thing is there, no? You have to click that.
custom slideshow you mean?
Sir, if you come down on the right corner, the percentage பக்கத்துல there is a full screen. You can see full screen. Okay, that you just
Down.
click, it will become full screen. Yeah, click it. That function is not happening.
Yeah, that one, sir. Yes. No, yeah. That one. Next to that.
A book type, sir. We can see all your five slides on the screen.
Yeah. But I am able to see in my computer it is showing full screen. I don't know why it was repeating. So in my computer I am seeing full screen, sir. I don't know why it is not coming in your screen.
Sir, we can see all the 5 slides, sir. I'm requesting the IT person, go down on the right side, there's a book type, click on that.
Book file.
Or you can change your setting, change the setting.
Yes. That one.
Reading view.
Yes.
That view.
Yes, sir. That one.
Click.
Now you are able to see.
Now full screen,
Okay.
sir.
Now it is okay,
this is
sir.
what we have been saying. Click பண்ணுங்க. Anyway, welcome once again. Let's begin. We have delayed by 5 minutes, so let's take it forward.
Okay, thank you. Sorry for the inconvenience. I am a novice in this subject, that's why. Sorry. So, starting again. So, this unearthed system is a system in which there is no intentional connection to earth. As you are aware, in an earthed system, we are intentionally connecting the neutral to earth. So, in an unearthed system, it is not done. The network will look something like this. Source may be a generator or a transformer, 3-phase or 3-phase 3-wire or 3-phase 4-wire, the distributed neutral may or may not, but the neutral is not connected to earth either directly or through any impedance. It is not connected to earth. This will be the typical arrangement of the unearthed network. But even when we say it is an unearthed network, whether you like it or not, there will be capacitive coupling prevailing between each conductor and the earth. Because as you know, two conductors separated by a dielectric is a capacitance, and wherever there are two conductors, two plates separated by a dielectric, a capacitance is formed. Here also in this network also there will be conductors, there will be dielectric. If you take a overhead line, distribution line, there will be a overhead line will be the one plate of a capacitor. Natural ground will be the another plate of a capacitor. The in between dielectric air will be acting as a dielectric, and there will be a capacitance formed. So there will be an imaginary capacitive coupling, even though we cannot say wired coupling. There will be a capacitive coupling throughout the system. it will persist. Even though we say physically unearthed, it will be capacitively earthed system. There will be a capacitive coupling. Any conductor, even you take a cable also, there will be a conductor and armor, and in between dielectric will be there. So wherever there are two conductors and a dielectric, there will be capacitance formed. In fact, all unearthed systems are capacitively coupled earthed systems only, to be more precise. So this will be like this. R phase with the earth will have a XC R, Y phase will earth will have a XC Y, blue phase will to earth will have a XC B. This capacitance will be there in the system. Capacitive coupling will be there. So in the, suppose we do not assume there is no earth fault in the system, the line to earth voltage will be equal, the three phase line to earth voltage will be approximately equal, because we presume that the capacitance is equally distributed. We presume, to simplify things, we presume that this is equally distributed. Now, do not think very complicated coupling, capacity coupling, all those things. Just look at this picture. If you say that this system is unearthed, the R phase is touching the metal of the load, metal enclosure of the load. A person is in direct contact with the metal enclosure. Worst condition, wet foot, barefoot, wet floor, all those conditions you assume. Generally speaking, there will not be any closed circuit here, because the person is standing on earth, but neutral is not connected to earth. So there is no closed circuit. So for a basic understanding, there will not be current flow through the human body, even in this condition. Leave alone high-end complicated subject of capacitive coupling. We will come to that later. But to start with, understanding a basic, since there is no closed circuit, there will not be any current flow, even in the case of a single phase to ground fault. We will come to the intricacies later. To make a start, we will understand that since this is a closed circuit, there will not be any current flow. So the current is a matter of, shock is a matter of current flow through human body. So let us make an understanding at present that since there is no closed circuit in this system, there will not be any, even though voltage is prevailing, there will not be current flow through the human body, and there will not be any shock. So the first big advantage of unearthed system is there is no shock risk, even in the event of a line to earth fault, assuming that the capacitance is negligible. Capacitances are negligible. If the capacitances are significant, yes, the capacitive discharge may affect the person. But to simplify things, we will assume that negligible capacitance is there. Now, even though the system is not connected to earth, a capacitive coupling exists between the conductor and earth, due to which, whenever there is a capacitance, there will be capacitive currents flowing in the system. So you can see when we have XCR, XCY, and XCB, you will also have ICR, ICY, and ICB. This capacitive currents will start flowing in the system through the earthed coupling capacitor. The capacitance earth of each phase is distributed evenly over its entire length, and for calculation purposes, we calculate as a single bulk capacitor. For calculation, simplicity of calculation, we assume this to be a bulk capacitor connected between each phase and earth. If the load is, we assume that the load is balanced and the conductors are symmetrically spaced. So when you under these conditions, since system is balanced and the conductor spacing is symmetrical, there will not be any residual fluxes, there will not be any residual voltages. We say that the neutral and the earth are at the same potential. Earth potential is always assumed to be zero. The neutral potential is also in this condition, balanced condition and symmetrical spacing, neutral potential is also zero. So we say that the neutral and the earth are equipotential points. So in such a case, neutral and earth potential are same. The voltage of each phase with respect to earth will be equal to voltage of phase and neutral. That is called the phase voltage. So now VRE is equal to VYE is equal to VBE is equal to phase voltage, that is line voltage by √3. Voltage across the capacitor will be equal to the phase voltage. That each phase and neutral earth capacitor will be impressed upon the phase voltage of the system. The capacitor current in each phase, ICR, ICY, ICB, we assume that this will be I, will be equal to V phase by capacitive reactance, which is equal to 1 by 2 pi FC, where C is the capacitance between the phase conductor and earth. This capacitance value will be very small, and the XC value will be very large because we say the dielectric distance is very high. So capacitance value is small. So since the capacitance value is small, 2 pi XC is 1 by 2 pi FC. So the capacitive reactance will be very high. Since the capacitive reactance is very high, currents are very small, negligible. These charging currents are almost negligible, equal in magnitude and 120 degree out of phase, and 90 degrees leading the voltages like this. You can see ICR is leading VRE by 90 degrees, ICY is leading VYE by 90 degrees, ICB is leading VBE by 90 degrees. Like the voltages, they are also 120 degrees apart. Now assume that R phase has got earthed in the network. Somewhere R phase got earthed. Now what happens? Since the XCR capacitor, top plate is also in R potential, bottom plate also in R potential, there will not be any potential difference in the XCR. So there will not be any current flow in XCR. XCR, both the plates are having the same potential. Since there is no potential difference, there will not be any current flow. But you can see XCY, ground side plate will be impressed upon R phase voltage now. Earlier it was neutral voltage or zero voltage. Now it will be impressed upon R phase voltage. So also for XCB. So the capacitances XCY and XCB will receive line voltage and not phase voltage now under this condition. That is what is explained here. Voltage VR will shift to the ground. Capacitance between R and the ground will be short circuited by the fault. The voltage across Y and B with respect to earth will now be equal to voltage between phases. As E is no more E has become R now. So VYE and VBE will become VRY and VBR, which is the line voltage, that is √3 times the phase voltage. Since the voltage, phase voltage has become line voltage, now you can see the current also will be leading the phase voltage by 90 degrees. That is ICY and ICB. ICY will be leading VCY, VYB by 90 degrees. And ICB will be leading VYB by 90 degrees. If you can see, the total net current flow during this fault current, the capacitive discharge current is the fault current. It is the vector sum of ICY and ICB. So IC1 and ICB, if you add the voltage, so since the voltage is increasing by √3 times, the current also will be increasing by √3 times. Earlier it was V phase by XC. Now it will be √3 V phase by XC. So the current will be no more I, it is √3 I now. Each ICY and ICB will be √3 I now. So if you vectorially add √3 I and √3 I, it will become 3I. So also earlier neutral and earth were at the same potential. So there was 0 volt between neutral. But earth is now R phase. So neutral and earth voltage will be neutral and R voltage. So neutral will show phase voltage now, because one end is R phase, earth is R phase now, and the voltage between neutral and earth will be voltage between R and neutral, that is phase voltage. So this is neutral will shift itself. No more, there will be huge voltage difference between neutral and the earth. Neutral will shift from its 0 voltage to equal to phase voltage now. And this will create its own set of problems. Now, the two capacitors will discharge into the fault, will feed into the fault, and the magnitude of the fault current will be equal to the vector sum of the phase currents, that is √3I and √3I, which will become 3I. Like this, in this triangle, you can do the trigonometrical equation. The vector AB will be equal to 3I actually. Now, you need not worry, even when raised by 3 times, the capacitor currents are still very low in magnitude. So the fault current is very low. Typical values are in 415 volt systems, they say it is about 5 ampere. In unearthed system, the capacitive discharge current, fault current will be 5 ampere. And in 11 kV and higher systems, it is typically about 25 ampere only. So no overcurrent protective device. You provide a overcurrent relay, you provide a short circuit relay. These relays are set to 100% and more. So this 25 ampere or 5 ampere, does not get sensed by the OCPD or SCPD in the system. So even in the, since there is no fault tripping, fault detection and tripping are not there, continuous supply, uninterrupted supply continues in the system. So this was perceived to be the second advantage of the ungrounded system. I say this was perceived. The very objective of the power system engineers will agree with me. The very objective of the power system is to supply electric power to the end user, even in the worst conditions. So even in the worst condition of a single phase ground fault, there is no interruption. Power supply will continue to go to the customer in ungrounded system. So not surprisingly, it was believed that in ungrounded system, there will be service continuity even when there is a single line to earth fault. So at least until the 1940s, perhaps until the Second World War, only ungrounded systems were popular. There are a couple of, the other day I was seeing a reference to some, this KHA techniques of Schneider Electric. In KHA techniques, there is a book on evolution of earthing. So that also very clearly says up to 1940s, these unearthed systems were very popular. But then, if it is so advantageous that there is no shock risk, current is not very high, fault currents are not, earth fault currents are not very high, and there will be service continuity, in spite of all these things, no, we do not practice unearthed system at all. We are much familiar with earthed systems. So there must be some disadvantage in the unearthed system. Let us discuss the disadvantages of the unearthed system. So the biggest disadvantage is during an earth fault, transient over voltage happens in ungrounded system. Let us analyze what happens. Under certain line to ground impedance condition, the ground circuit will contain inductive reactance and the voltage of the healthy phases may rise further. That is, it may even go to 5 to 6 times or more. Let us see. We call this condition as resonance and ferroresonance conditions. We will see how it goes. Also, this may tend to swing the system to an unstable state. There will be causing arcing grounds because the voltage to the earth keeps on rising. There will be a tendency for the arc to strike between the face and the ground or the face and the earthed conductor. So this will lead to the failure of support insulator and the equipment connected to the system line, align insulators and terminal equipment. There were reports of failure of equipment, insulators and all because of this arcing ground. So the magnitude of over voltage, there are precise calculations available which we will see, will depend upon the actual inductive reactance introduced in the circuit. What is the content of the inductive reactance? Now, the unintentional introduction of an impedance in a ground leakage capacitance circuit is a result of a ground fault in the main equipment such as generator, transformer or induction motor. When any of these windings get earthed like this. This is a network, there is a source and there is a load. If you can see, the one winding of the load has got earth fault is there. You can see the current flows, the direction of the current flows. There will be ICR, ICY, ICB, and through the load, there will be current flow. The capacitors will charge and discharge through the load. Capacitors will feed into the fault through the load now. Now, under such conditions, they will introduce their own inductive or resistive impedance or a combination of them into the ground circuit. Now, it is no more only capacitive current. It will be a mixer. It will be a series circuit of R and C or XL and XC or R, XL, XC circuit depending upon the proportion of the components. So, moreover, it need not be that the fault happens inside the load or the source. Even if there is any system fault in the network, there is a fault, the impedance will be introduced into the ground circuit like this. If you can see this circuit, in this circuit also the fault is not in the equipment. The fault is outside the equipment in the network cable or the network line. You can see here also the load inductance, the load impedance is introduced in the ground circuit. You can see the current flow diagram. But the capacitor will now how it is discharging into the fault. Now it introduces Yes, one more impedance apart from the capacitive reactance. It introduces one more impedance in the circuit. Depending upon the type of the load, it may be a resistive impedance, or it may be an inductive impedance, or it may be a capacitive impedance also. There are three possibilities, or a mixture of all the three. So now ground fault may be, so as you have seen in the above two diagrams, whether the fault is within the equipment or whether the fault is outside the equipment, there will be added impedance in the earthing circuit. So this added impedance, if you draw the equivalent circuit of the added impedance, you can see the voltage to earth is VL by root 3. There is a network impedance is there, resistance is there, and the ZG is the new impedance introduced into the ground circuit by the fault. So XCG is the ground capacitance. It may be XC R or XC Y or XC B. So you can see this ZG is the total impedance, sum of Z dash G plus XCG. Z dash G is the additional impedance introduced in the ground circuit during fault conditions. So V dash G is the voltage developed across the external impedance. Now we have three possibilities. Resistive impedance. If Z dash G is a resistive impedance, Z dash G is a inductive impedance, Z dash G is a capacitive impedance. Possibilities are there. So we will see what are the various transient over voltages developed under these three conditions. So under the above situation, ground fault within the load or ground fault outside the load, the ground circuit may give rise to dangerous voltages in the healthy phases. So the first situation is ZG is the external impedance introduced in the natural leakage ground circuit as a consequence of a fault inside the load or outside the load, either inside the load or outside load. Then the voltage across the external impedance can be calculated as per this formula. So VG max it will be 71%. See, it is simple mathematics. If it is 1.5 times XCG, it will be 83%. So if you see as R is voltage developed across the external impedance equal to root 2 VL. So this is not dangerous because this is designed for that. Any equipment designed for RMS value is capable of withstanding its peak voltage also. Next case is capacitive reactance. Assume that the external impedance is purely capacitive. So you can, instead of R, you put capacitance XC value. So the denominator XC by XC plus XCG. They will arithmetically add because they are in the same direction. They will arithmetically add. So here also you put various values for external capacitance. If the external capacitance is 0, if the external capacitance is 50% of the leakage capacitance, 33% voltage. If the external capacitance is 100% of the leakage capacitance, 50% voltage. If the external capacitance is 150%, 60%. If the external capacitance is 200% of the leakage capacitance, 67% voltage. So if you keep on giving values, if the XC approaches infinity, so the maximum value will be 2 root 2 VI maximum. Because if you see, as this fellow goes on increasing, this becomes negligible. This becomes almost 0. So 2 by equal to this 2 by 2 will be equal to 1. 1 into root 2 VI, the maximum value it can reach is root 2 VI only. Here also, like in resistive impedance, as XC approaches infinity, the maximum voltage, the impedance during fault, the load or the network will see is root 2 VI only, because that is also not to be worried, because this system is designed for withstanding a peak voltage of root 2 VI, VL actually. Now, the voltage developed across ground capacitance XCG and the external impedance R or XG is shared in the ratio of their own values, the sum total of which will remain constant at root 2 VI. Now, if you introduce an inductive reactance, if the external impedance is inductive reactance, which is the case in almost all the networks, because we use more of inductive loads in our networks. So the external impedance is predominantly inductive. Now the situation is different, because there is a possibility of XL resonating with the XC. We will see. Now inductive reactance, you put the same formula, XL by XC minus XL. Instead of R and XC, you put XL values here. Now the same formula. Now if you see 0 means 0, if external impedance or inductive reactance is 50% of the capacitive reactance of the leakage network, you see 100% root 2 VI is introduced. If the external impedance is 100% of the leakage capacitance, so XL equal to XC. Whenever XL equal to XC, it is called a resonance. So you can see the voltage is almost infinity. It is not practically infinity, because the network also contains some resistance. So the resistance to an extent reduces, but it is very high. Whenever the external impedance happens to equate the leakage capacitance of the system, there is a tendency of the voltage appearing across the external load going towards infinity. That is, very high voltage will be thrust upon the equipment and system during single phase to ground fault in an unearthed system. So this is known as resonance condition. It is however seen that in view of the some inbuilt resistance in the ground circuit, it will be attenuated, not practically infinity. There have been calculations. It is seen that the voltage will float between 8 to 10 times the root 2 VI. This has happened because our equipment are not designed for withstanding this voltage. So there is a chance of equipment damage and system damage. So this will tend to voltage raise the ground potential substantially depending upon the value of the external impedance. So it will also raise the potential of the healthy phases, which may cause arcing grounds and become dangerous to the line insulator. This is called resonance effect. Further, if you increase it, suppose if you keep on increasing, you see it starts coming down. It is like an inverted parabolic curve, starts from low value, go to a peak and coming down. So if it is 1.5 XG, it is 300%, 2 XG, it is 200%, 3 XG, it is 150%, 4 XG, 133%. So if you keep on increasing, it will start dropping down. So one particular resonance, it will high. So when you keep it infinity, again as seen in the case of resistance and capacitance, it will maximum come back and settle down at root 2 VI. So the danger here is whenever the system network inductive reactance is equal to capacitive reactance during an earth fault, there will be very high over voltage thrust on the system, which is not good for the system. So the disadvantages, summing up the disadvantages of the unearthed network, as we have seen in the previous slides, there will be huge transient over voltages during a single line to ground fault, causing damage to system and equipment, because we cannot design our system to tolerate this high voltage, because it will make our system and equipment costly. So we generally economize in our design. So when we design our system for tolerating nominal over voltages, when unearthed system, when this happens, system and equipment get damaged. So even though next we said that there will not be any power interruption during a single line to ground fault. So it is a big advantage. Practically, it is not so. Even though the single line to earth may not cause a power interruption, it will cause a second line to earth fault sooner than later, because the ground potential has now become phase potential during a single line to ground fault. Then the second phase and the third phase to earth voltage has increased, its insulation will be stressed. So sooner than later, a second line also will get grounded. There have been instances of immediate second fault in the system. So the voltage of it will soon cause a second line to ground fault, as the voltage of the healthy line to ground during the first line to ground fault will have increased by √3 times. Thus, the insulation phase to earth insulation of the healthy phases is stressed now, because the voltage has increased, it is stressed. So more sooner than later, there will be a second earth fault. Whenever a second earth fault happens, the fault becomes a line to earth fault. It is no more line to earth fault. It is line to earth fault. It is double line to ground we call. Now, the system OCPD may not detect a single phase to ground fault, current is negligible. But when this becomes a line to line short circuit, definitely the currents are huge. So definitely the system OCPD or SCPD, over current protected device or short circuit protected device, will operate, as the face to face short circuit current is very high, even in kiloamperes. So definitely there will be a power interruption. So whatever we have earlier told, initial for understanding, we told the advantage of ungrounded system is no interruption is lost. The advantage is lost. So because single line to ground fault will never remain single line to ground fault, it will soon culminate into a second line earth fault, ending up in a line to ground fault. So this line to line fault is current is more, and the breaker trip or fuse will blow, causing interruption. So that advantage is definitely lost. And as I said, arcing grounds, because there is a potential jump, it will cause between earth and healthy phases, it will keep creating, trying to strike an arc. So these arcing grounds are also causing damages to insulators and the terminal equipment. There are records of damages caused to terminal equipment and insulators. So this is another big disadvantage. And if you do not want to if you want to avoid these damages due to over voltages or higher voltages, you generally have to design the insulation for line voltage and not for phase voltage, because during earth fault, these healthy phases will see a line voltage. So generally you have to design your system for line voltage. That is why they say unearthed cables, cables for unearthed system and cables for earthed system. So cables for unearthed system are generally costly. If they say 11 kV E or 6.35 kV UE. So in fact, for 6.6 kV UE system, you have to practically use a 11 kV cable. So 11 kV E is equal to 6.35 kV UE system. So every time an unearthed system is there, you have to use a higher rated cable, higher rated equipment. So that will make your system costly. Similarly, when you see the PT standard, potential transformer standard, the over voltage factor is very less for grounded systems. If you see, it is for solidly earthed system, it is 1.2 continuous and 1.5 for 30 seconds. So if you see the unearthed system, it is 1.2 continuous and 1.8 for 8 hours. So if you order a PT with a higher over voltage factor, it has to withstand 1.8 times the rated voltage for 8 hours. Definitely the CT will be costly. CT will be bulky and costly. If you want to use the PT in unearthed system, definitely you must go for over voltage factor of 1.8 for 8 hours. Similarly, if you see the surge arrestor rated voltage calculations, it depends upon something called a ground fault factor. The ground fault factor is a 0.2 for solid 0.8 for solidly grounded systems, and it will vary from 0.8 to 1.732, as high as it is 1.732 for unearthed systems. So definitely for unearthed system, if you want to use a surge arrestor, you have to use a higher rated voltage arrestor, which will make the arrestor bulky and costly also. So these are the some of the disadvantages of the unearthed system. Sorry. So because of the above disadvantages, because people later thought it is easy to manage current than to manage voltage. So people thought that earthed systems are better. So the world also moved towards earthed systems. From unearthed system, world slowly moved towards earthed system, and predominantly we can say that most of the countries follow earthed system. It could be directly earthed, or it could be resistance earthed, or it could be impedance earthed, reactance earthed, or Peterson coil earthed, or whatever may be the earthed system. Most of the networks in the world are today practicing earthed system only. Unearthed system, yes, there are certain installations where service continuity of paramount importance, say in hospitals, maybe where operation theaters or critical diagnostic equipment are there. They don't want the power interruption during a surgery or during a diagnostics where the results may be tilted. So people still, for locations where service continuity of important, they go for unearthed system. The network is split. In such cases, the network is itself is split with separate transformers. One transformer with earthed system for normal system, one transformer with isolated neutral for special areas like hospital, operation theaters, diagnostic rooms, and certain nuclear establishments also. They want unearthed system. They don't want supply continuity to be disrupted. So unearthed systems are now confined to very minimal locations. So maybe in a subsequent seminar, we will slowly graduate into discuss the various advantages and disadvantages of each method of earthing, like resistance earthing system. What are the advantages, disadvantages? The reactance earthing system, what are the advantages, disadvantages, and the analysis? Like we have done the analysis for unearthed system now, we can also do the analysis for resistance earthed system, reactance earthed system, that is low reactance earthed system and high reactance earthed system, which is known as Peterson coil earthing or arc suppression coil earthing. Maybe I think maybe a month from now we may conduct a second webinar, in which we will discuss the earthed systems more elaborately. Now I think I am open for questions now.